Welcome to the video. When setting up a static general step in Abaqus, there are 4 key settings in the Basic tab that you need to understand. In this video, we'll explain each of them in detail, so if you're using the static general solver, be sure to follow along. First, there's the time period setting. This defines the total time of the phenomenon you're modeling in this step. If your problem is rate dependent, which means it involves material behavior which changes with rate of deformation or includes damping, you'll need to enter the real time of the process here. But if your problem is rate independent, like most simple cases, just enter 1 to keep things straightforward. Next up is nonlinear geometry. You can set this to either on or off. If you're dealing with small deformations or small linear elastic structures, you can leave this option off because the calculations will be based on the initial configuration. However, if you're dealing with large deformations or large rotations, you should turn nonlinear geometry on. In this case, Abaqus will calculate based on the updated configuration throughout the solution. The next option we'll look at is automatic stabilization, which helps handle unstable nonlinear static problems. These instabilities can come from various sources, such as geometrical instability or material softening. When the problem shows a negative stiffness in its load displacement response, it's considered a buckling or collapse problem, which can be solved using buckle or Rick steps, as we've explained in previous videos. However, when the instability is localized, where strain energy transfers from one part of the model to its neighbors, standard global solution methods may fail. In these cases, the problem needs to be solved either dynamically or by adding artificial damping. There are 3 options available to address this. The first method is defining damping with dissipated energy fraction. This method calculates the damping factor so that the energy dissipated is only a small fraction of the extrapolated strain energy in the first increment. This fraction is called the dissipated energy fraction, and the default value is 0.0002. If you use the adaptive automatic stabilization scheme, the damping factor is adjusted based on the convergence history and the ratio of energy dissipated by viscous damping to the total strain energy. If the convergence is unstable, Abaqus standard will automatically increase the damping factor. You can set an accuracy tolerance for this, with the default being 0.05, which works for most cases. In the next method, you can directly specify the damping factor. In this method, you manually enter the damping factor. However, estimating this value can be tricky unless you have data from previous runs. The damping factor depends not only on the level of damping, but also on the mesh size and material behavior. The last method is to allow propagation of damping factors from previous step. In this method, the damping factors from the previous general step are carried over to the following steps. You can find a complete guide on setting damping parameters and analyzing their impact on the results in our next video. The last option is adiabatic heating. This comes into play when mechanical deformation causes heating, but the process happens so quickly that the heat doesn't have time to spread throughout the material. A good example is a high-speed forming process. If you want to account for this effect in your simulation, make sure to toggle adiabatic heating on. You can also check out the example simulation with adiabatic heating in this video. Don't forget to like, subscribe, and click the bell icon to stay updated on our latest videos. We'd love to hear your thoughts, so drop a comment below. Also, be sure to visit our website for more related products and resources. Thanks for watching, and have a great day.